Let me Hey, hi, everyone. So, it's my great pleasure to have Dr. Yuri Lensky from Google Quantum today. So, Yuri graduated from Stanford. I was actually his PhD advisor. I learned a lot from Yuri, and we brought quantum chaos and the quantum gravity, black holes, and second model, a lot of things related to this. And it seems like neither of us remember which year he graduated. And then Yuri is a base fellow in Cornell University, where he started to work on a very different area of quantum computing and quantum error correction. Very quickly he becomes the expert in this field, and then they started some really interesting works on computing in circuit code, and as a consequence, very quickly Google successfully grabbed him, and so he would Google quantum for like 3 years, 2 years. So today we will talk about K series and
yeah, thank you very much for the nice intro. So yeah, just to be very clear, like you please feel free to interrupt anytime with questions. We don't have to get through everything. So yeah, this is what the talk is about, and it's kind of about the fact that these kind of abstract, it's kind of amazing with these early quantum processors, how much we're supposed to use quantum processors to learn about quantum theories, but actually right now the exchange is going a lot in the other direction. Abstract ideas that we got from studying low-dimensional field theories and discrete gauge theories actually tell us how to use the quantum processors. It kind of goes in the other direction. So here I tried, it's on my signature, as Sean suggested. I tried, this is supposed to say both learn and teach. If you look at it, but there's a problem. There's a problem with locality here because the point is that this first letter should be an L or a T, and then for learn and teach, and this needs to be CH or RN. But the problem is that it just looks like leech if you make it.
I thought that was your credit card signature. I couldn't get that.
Yeah, this well, it won't work if people check.
It's a noisy.
Okay, so the point is to talk about how ideas from 2+1 lattice gauge theory actually inform us how to use the quantum processor. And I'll talk about 3 experiments. And again, I just want to emphasize that only the last one, this confining gauge, these are all either on the archive or published. This example where we study confining Z2 gauge theories is actually the only one where we're starting to use quantum processors to learn about 2+1 decay theories. These 2 examples for topological quantum matter and disordered quantum systems are examples where ideas from lattice gauge theory actually teach us how to use the process. So the bulk of the talk will be about this. This is really all we're going to get through. If there's time, it would be great to talk about these 2. I want to emphasize that most of the discussion will be theoretical, but these are all experiments that have been run. They're all about experiments that have been run. So topological quantum matter, and in particular, the theory of non-Abelian, simple non-Abelian anyons, informs us a lot about how to build a robust quantum memory, and we actually use ideas about non-Abelian anyons and topological physics very, very directly. A very direct simulation of these topological phases, and in particular, Abelian and non-Abelian anyons play a huge role in error correction. And again, this will focus on, and error correction includes memory and gates. So the next topic is disordered quantum systems. So there's many interesting things to ask about. Many-body localization and the study of rare events are kind of central to the topic. Something which is a little bit more unfamiliar and kind of interesting is that you can actually have localization without disorder. And gauge theory kind of gives a very clear explanation for how to efficiently implement something like that. And finally, if there's time, we'll talk about confining Z2 gauge theory. And this is just a path for studying certain aspects of Z2, well, really highlighting which aspects of these confining Z2 gauge theories are convenient to study on early quantum processors. So, apart from this section, most of this will be about what we can do on quantum processors before error correction. Okay, so I work for Google, and at Google we have something called a transmon qubit. And so the way that these qubits work, the whole idea is that we have a very controllable quantum system, and you have to think quite differently about how to use these things. So an LC oscillator, you might remember from high school, is, well, just a harmonic oscillator. And interestingly, you can just quantize this kind of directly without thinking. And you do get an oscillator. And if you have to build it out of superconducting components, there's no loss, and it's a very good quantum system. And it really is a very good oscillator, equally spaced energy levels. And this is great and very interesting, and you can do experiments with arrays of these things. But actually, this is a problem if what you want is qubits. So qubits, a two-level system, is very convenient to control for many other reasons. And so you have to add some anharmonicity. You can't have equal level spaces because otherwise you'll drive every transition at once if you try to drive the system. So what we do is we have something called the Josephson junction for nonlinearity. So this is a layer of superconductor, this layer of superconductor. And this you can just think of as giving you nonlinear inductance. And so for many experiments, we restrict the qubit levels, although I do want to advertise that we can go to use the two-state as well for experiments, and there's some small anharmonicity. It's actually very small in these spaces. And then if you're interested in the readout, we have these sort of long resonators. We dispersively couple to these resonators to reflect microwaves off. And so there's control by microwave drives. But these are all sort of technical details, and you can think of kind of an abstraction that we have 100 qubits with readouts, and they're locally coupled on some square lattice. This is a picture of an old chip. And in here are the qubits. These are wires that we use to control the chip. And there's around 180 qubits, which act as couplers. So we have an array of qubits with readout, and then additional qubits that we control with couplers, and that's how we turn things on and off on the device. We can operate either in digital or analog mode. This talk will be all about digital operation, but we have several papers about how we operate analog. The distinction between these two is that here, the system's in the digital operation mode, you really can mostly think of a circuit picture. And in analog, we sort of turn on the whole system and let it evolve. Again, we won't talk about analog in this talk. Okay, great. So that's the physical device, and we want to be able to work with it. And so just a quick review of gauge theory for people in the audience. So gauge theory is a theory, roughly speaking, with local symmetry. And the thing to remember maybe is from electromagnetism, this side is about electromagnetism. So the vector potential is in some sense unphysical. What that means is that you can shift it by a gauge transformation. Nothing is supposed to change. But still the vector potential is motivated because you want to have a local description of certain physics. So the most striking example of this might be the Aharonov-Bohm effect. You have some localized flux and you take a particle around the flux, or you do an interference experiment. There's no flux outside, so there's no local theory of fields. If you just have fields, there's no local theory that explains an Aharonov-Bohm experiment. But there is a local theory that explains the vector, that explains it if you include the vector potential. Now, the Gauss law in these theories is a constraint. This equation doesn't involve time, and actually on the right-hand side, you can just put a background charge, which won't evolve. And so in quantum language, this means that this constraint should commute with the dynamics, with the Hamiltonian. Now, there's two ways that a gauge field can show up. One is kind of dynamical. This is you imagine that you're modeling both electromagnetism and your matter all together. But actually, if you have a background gauge field with fluxes, so again, a very good picture is Aharonov-Bohm, and we'll come back to this example over and over and over again. A background gauge field with fluxes will still motivate you to introduce a vector potential because you have this background gauge field, you still don't have local fields. You don't have any fields locally to the particle, but they're still sensitive to fluxes in the center. So this is called a background gauge field, and then these we'll call dynamical gauge. Okay, so how do dynamical gauge fields look on the lattice? What we imagine is we have vertices, and here we'll do just a pure gauge theory in this picture without matter. So we would have matter that lives on the vertices. Here we just imagine that there's no matter. And then these blue things are qubits. So this will be a Z2 gauge theory. And the Gauss law, this constraint, just turns into a projector. So we might take some single qubit operator here, we've chosen X. We go around the vertex, and for each qubit that touches that vertex, we put an X operator. And our condition for gauge invariance, this condition, is just that the state is an eigenstate of eigenvalue +1 of this operator. And that's going to be our local symmetry, and all the dynamics has to commute with such an operator for every vertex. Okay, there's also magnetic fluxes if we choose X's here. then a natural choice here is z's. So these operators, the fluxes, they're examples of legitimate gauge invariant operators because they commute with the gauge constraint. And the reason is that for any loop, so for any loop, we write down the product of the z's. And for any loop, it touches every vertex, every black vertex, an even number of times. So, and again, feel free to interrupt, but this is just sort of a quick lightning review of gauge theory, but it plays such a big role that I think it's worth it. So, okay, we're starting with the first topic I mentioned, which is, really you should think of it as a gauge theory for qubits, and everything else kind of just falls out for free. So let me just kind of reemphasize again how gauge theories work in reality. So here, the point is that we actually have a real gauge theory. Like, it's not one that we simulate. There's actually an emergent gauge description. And so let me remind you how it happens in, for example, electromagnetism. There's no vector potential in the universe. You can't measure it. You introduce these degrees of freedom by hand. And what that means is that, somehow along the way, it feels like you're making choices. Although at the end, it feels like you didn't because the description kind of works so well. So nature doesn't dictate these extra degrees of freedom directly. You have to sort of know from desiring certain features of an explanation of your theory that you should introduce these degrees of freedom. But still, if you notice something that looks like Aronoff bone, then that suggests to you that maybe there's a good gauge description. And you notice some properties of your degrees of freedom that they behave like something. And then you just insist that they are, and you gauge out the unphysical pieces. So again, the example is Aronoff bone for the vector, always. Here we'll see that for qubits, we actually have a Z2 times Z2 gauge theory of 4n Majorana fermions. Now, there's 2 Z2s instead of 1. And what happens is that we take the qubit and we embed it into a set of 4 Majoranas. And we have a usual fermion parity projection on the qubit, which reduces the space. So 4 Majoranas give you actually the space of 2 qubits. And one of the projections brings you down to the space of qubits. But actually, you have several choices that I'll explain to do with these arrows and colors. And if you treat this thing very carefully and you consider interqubit operators, you end up with the Z2 times Z2 gauge theory. And so this is going to be most of the work to get to 1. And then I'll convince you of 2 by giving some examples. But once these 2 are kind of accepted, these consequences just fall out. You just immediately get surface codes that come directly from this gauge description for no additional work. And all you do is you just remove the fluxes. You just see that correcting errors is keeping track of the fluxes of one of the Z2. And moreover, as I'll explain in a second, these Majorana fermions are bound to a flux, and flux-bound Majorana are the simplest example of non-Abelian anyons. And so immediately, just from sort of the structure of the description, you instantly get non-Abelian braiding, an efficient non-Abelian braiding inside of qubits. Okay, so that's where we're headed. But let me just sort of explain. So maybe the focus is going to be on the non-Abelian braiding itself. And, yeah.
So the
one of the Z2 is the fermion parity. And you can think of one of the Z2s as the fermion parity, and you can think of one of the Z2s as sort of the Z2 of the surface code, but not exactly. And I'll explain how that happens.
This is going to be a new family of models, or no?
It's a new family of models that includes the surface. So, and just to sort of emphasize the point on non-Abelian braiding and what can happen. So in order to explain non-Abelian braiding, maybe people that haven't seen it before, you have to explain what a non-interacting particle is. So what do we mean exactly by non-interacting particles, and why is non-Abelian braiding surprising? What we mean is that we might have, 4 particles in a row. And if you look at one of them, say the third one, well, if you do when we say that they're not interacting, if you can do any experiment inside of this region, and you can't tell where the other particles are. You can't tell an energy shift, there's nothing. As long as you look locally, it doesn't know about any of the other particles. Maybe it knows some global feature like their parity, like maybe there's even numbers, so you know it has a partner. But you don't know anything about the other particles. And this is actually an important feature for error correction as well. But let's see what happens when we have non-interacting particles. So maybe we have two non-interacting particles, which between them share a degree of freedom. So, jumping ahead a little bit, that's like the fermion degree of freedom between two myrons. And, maybe you measure some observable between them and it comes out blue. Okay, and now they're able to interact in this tiny little circle and you measure something. Now you separate them. And now the particles will stay separated in this region. And so the naive expectation is that if you separate them, you kind of do this adiabatically and nicely, this particle doesn't know about these guys, doesn't know about this guy. Okay, great. You bring them back, and if you did everything nice and smooth, this thing doesn't look. If there's sort of, you turn off any weird stray interactions here, you separate them, and you let it rest, you bring it back. Nothing much can happen. And the point is that if you do this, and now you can ask, well, what happens if instead I bring it around the particle? Well, this central particle here could have stayed outside of the radius of this guy. So nothing should happen. They're not interacting. So it should be insensitive. And, for almost all particles that you're familiar with, if they're not interacting, if you had blue go to blue in the previous case, this doesn't change anything. You bring them around and blue goes to blue. But actually, the whole interesting thing is that for something called non-Abelian anyons, this observable can flip, despite the fact that these are kept far apart from each other. This is actually what gives them an interesting error correction property. And I'll talk about that in a second. But I just want to emphasize that, if you want non-Abelian anyons, so there's a few key ingredients. You need non-interacting particles, otherwise the effect isn't that interesting. And it's best to have classical information about the particle location. You want to be able to localize it very much so that you know what you're doing, see what's happening. And this is the last important one, but I really want to emphasize it. You need locality in two spatial dimensions. This means that if you want to actually demonstrate the phenomenon, it should be like our quantum processor, which is a 2D chip, where there's a real sense of locality actually in the system. You can sort of simulate the multiplication of these matrices, but it's locality in two spatial dimensions is extremely important to actually demonstrate this. Okay, so let me sort of skip to the end and say that here we identify, and I'll explain later in the talk how to do this. These triangles are the classical locations of these non-Abelian particles, and we move them. The blue squares are kind of us keeping track of the background on which they're moving. They're kind of moving on the canvas. We're keeping track of the background. We actually didn't have to, but we choose to. So for error correction, we would have, but this is not an error corrected experiment yet. So what we do is we take this guy and we move him across the edge. And then one of these, this one comes up, and we do some fancy braid. It takes some time to keep track of the particles here in this picture, but you should just imagine that what we do is we create them in pairs here and here, and then we take one around the other. And what happens is that something that used to be a vacuum ends up being a fermion. And that's the meaning of these red squares over here. Okay, this is experimental data. We've done the experiment, but the point is to explain why something like this works and what we really mean by all these blue squares. But again, just to sort of re-emphasize, what we mean here is that these blue squares, I haven't told you what operators we're measuring, but it's operators that are local to these squares, and they give you classical information on where the particles are. All right, so now let's get a little bit concrete. Let me remind you quickly of the Majorana algebra. So the Majorana operators are actually just defined as some reduced representation of this algebra. So they're Hermitian and they anti-compete in this way. Okay, so two of them, they're kind of like the square root of a qubit. Two of them define a complex fermion, and you can see the irreducible representation for n of them. Well, we'll always get n because the right symbol. But in this sense, they're half a qubit. It's 2 to the number 2 rather than 2 to the power. Two of them share a complex fermion. Okay, now we're just gonna draw pictures. These are, we're gonna sort of try to stay away from equations. And the way that we're gonna focus on pictures is that we're gonna draw Majoranas mostly as these dots, or there'll be vertices in various graphs. And there'll be links between them. And on the link, you should imagine that there lives a particular operator. This operator is this bilinear. It's a product, alpha 2, alpha 1. Because of the ordering, we have to put an arrow. This arrow will actually seems benign, but it plays a very big role in what we'll talk about. But to define the link operator, we have to put an orientation. And that orientation, you can think of as either a fermion parity. So for example, for this fermion, if I define it in terms of alpha 2 and alpha 1 site, then this is the fermion parity operator. It's +1 if there's no fermions, -1 if there's one. Or you can think of it as kind of like a Pauli matrix. Well, at least it squares to 1. Now, okay, and one other thing I'll mention is that if you have a network of these, then if they touch in one place, then the operator is anti-commutative. Otherwise, these operators commute. So that's Majoranas. Now, first, let's talk about why it's important that they're the square root of a qubit. Well, actually, flux-bound Majoranas will do exactly this thing. So this blue line that you saw before is the shared fermion between them, the shared fermion parity. And they can be non-interacting. And one can go around the other, and you can measure the fermion parity between them after, and you get a sign flip. You get an extra. Now, how could this possibly happen? So there's a paper written in 2001, which is very nice. And this explains the non-Abelian part of the statistics in terms of, again, local understandable physics. Actually, it's not surprising once you see the explanation. What happens is when you drag this particle, well, this fermion parity operator actually corresponds to a Wilson line in C2 gauge theory. These two Majoranas are bound to some flux, in fact. What happens is when you drag one particle around, you can imagine that this operator, which should be +1, which measures the fermion parity between them, gets stretched into this Wilson here. And just like the normal Aronoff-Bohm effect in typical gauge theory, the difference between this red line and this blue line encloses a Majorana, which is bound to a magnetic flux. And so this Majorana operator picks up minus sign because of this, because it went around the flux, the Z2 flux, and it flips the parity over here. So I think that's exactly what I said over here. And this is exactly our mechanism. So again, the physical model that people had in mind before were vortices in a people's IP superconductor. These vortices also trap Majorana, and because it's bound to flux, you can give an explanation of the non-Abelian braiding system in that system. And the point is
here you're talking about
yeah, and in the people's IP superconductor, it is Majorana bound to something that you can consider to be a Z2 flux.
Yeah, but I just want to say that's different from, that's a different state from this state you're talking about.
Which state?
The service.
Oh, no, the point is that that's what it's going to become. It's going to become something like this. There's an extra Z2. So there's an extra Z2 gauge field. But one of the Z2 gauge fields is the gauge field that these Majoranas are bound to a flux of. So in the surface code is actually exactly this system, except there's an additional Z2 gauge field with its flux. So this system has a single Z2 gauge field, and that gives you non-Abelian braiding statistics. Our system has two Z2 gauge fields. One of them is exactly like this, and you can actually imagine just piling on a second Z2 gauge field. And that one, of course, fluxes of that gauge field will correspond to errors. But actually, if you have no errors, you can just imagine that gauge field is always in the back.
I guess I'm confused because that's a parallel state. What you have is not a parallel state. So
That's true.
Probably.
Oh, so yes, okay, so yes, that's a very good point. We actually have we have only the two gauge fields I described, but actually there's a partner to every Majorana. So every Majorana is a partner, but the number of gauge fields is still 2. And you can, if there's no errors, you can still ignore one of the gauge fields. And the other one behaves like this, except you have 2 Majoranas. So it is a non-parallel state, that's right. In our case, we can actually detect one of the other copies. And that's why, so I won't maybe talk about it in those terms, but I'll explain it when we come to it. You can actually detect which copy you're in, basically, and which chirality you're in. And so we can always restrict ourselves to a single sector. Okay, so let me talk quickly about an error correction perspective on all of this. So there's a theorem called Nil-Laflamme, which says that in order to do error correction, roughly speaking, this is a generalized monogamy statement, and we can talk about the precise version of this theorem maybe after the talk if anyone's interested. But pretty much it says that if your environment learns anything about your quantum computer, that bit is not used as a bit in your quantum computer. And so the key idea is to hide the quantum information on your quantum computer from the environment. Now, how can you do that? Well, we were talking about these particles that aren't interacting locally. And so what happens is that errors occur locally on your system. They can only do local, the idea is that they can only learn local coherent information. And if the particles are separated, they can't learn their fusion channel. So that information is hidden. And Kitaev had two beautiful insights. One of them is that by separating particles, you could accomplish this. But the second thing is that it seems that you solved one problem, which is protecting information. But now how are you supposed to compute on information you've hidden from the environment? You can only do local operations as well. So how can you operate on the information you've hidden? And Kitaev's answer is that actually what you can do is you can operate on this thing by doing sort of the only operation that you can while keeping the particles separated, which is braiding. And so we're going to talk about gates by braiding. You could view this talk as kind of demonstrating those ideas experimentally. So, okay, let me just say that, re-emphasize again, that all we do, so the next couple steps, we're going to go from qubits to Majorans. This is like, again, looking at electromagnetism and introducing a vector potential, and then just seeing what you get, and seeing consistency with the basic gauge fields. So we'll find several gauge fields, and I said, yeah, so one of these gauge fields wasn't involved in the previous P plus IP example. The other one is the one in the P plus IP example responsible for the non-Abelian statistics. You find several generalized surface codes. We actually, our topology is always trivial. We're not building toroidal chips yet. So we see that surface codes and generalized surface codes, at least as they're used today, only store information in two ways, which is topology, which we don't use, and Majorans. They're already there, so you might as well use them. And locally, you should just think of the surface codes. So, you know, we do this embedding into Majorans, but locally, you should just think of the surface codes as like kind of this canvas, and you just plop Majorans on there, moving around, play with them. This includes lattices, you know, for experts, and I'm happy to talk about it after the talk, although not during. This includes operations like lattice surgery and, you know, fusion measurements. But here we'll talk about unitary operations by braiding. Okay, so
this is also going to allow you to get large code rates with all different.
it lets you get larger code rates, but you can't violate. I mean, so we can't. Majorans don't let you violate theorems. So in 2D, you don't. The surface code is still optimal in terms of scaling, but you do get higher. I won't talk about that here, but actually you can get quite significantly higher code rates, but again, not asymptotically, not in terms of scaling, but in terms of order one factors. Okay, so let me talk about the concrete embedding and actually start to see these gauge fields pop up. So now we have, you know, the Pauli algebra X, Y, Z, naturally 3 anti-commuting operators, and it's, you know, very natural given these Majorana operators to assemble them into this triangle. Now, the operator on the yellow edge, the green edge, and the blue edge, they all anti-commute with each other, and they all square to 1. So, naively, they seem that they almost satisfy the Pauli algebra, except you have to check one thing. Oh, so yeah, 3 operators that all anti-commute and square to 1 must be unitarily equivalent to the Pauli operators, except up to some signs. So, there's a constraint that the Pauli algebra satisfies, which is that the product of x, y, z is I, not minus. And so that forces a particular orientation of these arrows. So here, no matter what arrows I pick, these 3 operators will anti-commute and square to 1. But their product in some order could be plus or minus I. And so if I want to make this assignment, x, y, z, I have to choose the arrows, it turns out, such that an odd number are thoughtless. And this is a Castellan orientation. It'll turn out to be very nice and geometrical for us. Again, for the experts in the audience, the Castellan orientation is a discrete version of something called a spin structure. Now, to have a local embedding, you don't have some irreducible representation of 3 Majoranas, you have to have 4. And this is convenient for other reasons. And so now let's look at what happens when we have 4 Majoranas. So a single qubit, we might want to embed it into 3 Majoranas to get a Pauli algebra, but actually let's embed it into 4. So here, the blue line doesn't touch the blue line, and the yellow line doesn't touch the yellow line, and so on. So if we make this assignment around one face, well, this blue line should be Z, but this blue line, well, it commutes with Z, but it anti-commutes with this green and this yellow line because it touches them. So its only choice is to be Z times something. And we just choose the arrows always so that these are the same operator. Okay, so actually this seems pictorial, but you know, it seems that maybe this is maybe too pictorial, but actually it specifies a concrete embedding from a qubit to the space of 4 Majoranas, just by this operator and the arrows. The arrows are important. So what's the sort of global structure? Well, if you make a little tetrahedron for every single qubit with these arrows and the colors, let's say that blue is always X and green is always Y and yellow is always Z. If that's the choice I make here. No, sorry, blue is always. It won't be too important. So when we do this, at each qubit, we specify a concrete map from C2 to the N to C4 to the N. Okay, so this space is too big. So it's some metric embedding. And the way you should picture it is that this big square, this big box, is the space of all of my Majoranas, 4 Majoranas per qubit. And what I've done is I've chosen some subspace of C2 to the N, a physical subspace where the qubits live. Now, there's some projection. So for each qubit, there's a local projection. And this projection will basically enforce that the blue lines are the same operator. That's the fermion parity projection. And that tells you where the physical space sits. It tells you where this gray region is. Yes.
So I mean, in the previous case where you had just a triangle, the 3 Majoranas,
Yes.
you sort of had this constraint on the arrows having sort of an even number of clockwise.
Yes, actually, that extends to every face here.
But does it? Because if I look, for instance, here at like the very bottom face of 3 Majoranas, like don't I see that sort of has a loop?
You're looking at it from the wrong side.
Oh, I see.
So it's every face. It's every face viewed from the outside.
I see.
So actually, I'm very impressed with your counting because I take a long time to do that, but nice. And thank you for checking. But yes, if you look from the other side, it actually works.
Okay.
Thank you. I actually wasn't sure if those were right. Anyway, so there's this projection, and what happens is that tells you. So we have some map from C2 to the N to C4 to the N, and so we have to find where it ends up, and where it ends up is given by this projector. So this projector goes from this space, from this gray space down to C2 to the N. So this is this gauge theory projector, and this tells you where the physical space is. But actually, even after you choose the space, you have to choose how you sit inside of that space. And that additional information is in these arrows. So the arrows kind of like this tetrahedron tells you a specific embedding. It tells you both where the space is and how you sit inside of the space. And this gives rise to 2 gauge fields. This gives rise to a dynamical gauge field, which is a real gauge field kind of in the theory, which is associated to this Gauss law, this projector. We'll see how that shows up. But we still need to fix how this lies in this gray space. There's still multiple choices. Even if you insist that this pair and this pair give you Z or X, you still have several choices how you sit in this space. And this gives a background gauge field. And this background gauge field you should think of as associated to these arrows. This dynamical gauge field you should think of as associated to the fermion projector.
Sorry, I can just zoom out for a second. What's the problem you're trying to solve relative to existing folks? Like what's the future they have that?
So specifically in the surface code, in architectures, in qubit architectures, what is the most efficient path to non-Abelian gradient? That's one problem, although there's several, which is, for example, understanding more dynamical codes compared to the surface code. I can talk about practical implications after, but maybe for this talk, just imagine that we want to somehow do non-Abelian gradient. We liked the Majoranas, and now it's kind of like, I can't unfortunately, I don't know a better way to go through this story than it's like when you're teaching electromagnetism, you kind of just say, here's the vector potential, and then let's look. And that's kind of what's happening. So let me give kind of a map of what's going to happen, actually. So we have a qubit. We embed that qubit into 4 Majoranas. Now, most of the time, I'm going to suppress these green edges and just take sort of a rotated version of the tetrahedron and draw just the yellow and blue lines, okay? I sort of haven't lost any information there. And actually, this still satisfies the path. Now, let's go through very carefully sort of what choices we have. When we went from the qubit to this tetrahedron, actually, we could have chosen around each face any permutation of the pallies, X, Y, Z. That gives us an S3. And then we could have chosen all these arrows that come into, let's say, the top vertex. That gives me a Z2 to the third. Okay, that's the choices of this embedding. Now, actually what we'll do is we'll insist that basically X, Y, Z are in some the correct cyclic ordering around each face, that moves us down to Z3. And that's the same as the Castellan condition. And still we have a Z2 cubed because I can choose any of these 3 arrows going to this top vertex and that fixes the bottom, according to the Castellan condition. So I have a Z3 times Z2 to the third. And okay, now what's interesting is that we can go a bit further. And what happens is we introduce now additional degrees of freedom. So what we do is we add these black lines. That doesn't introduce an additional degree of freedom, but we add something unphysical, which is the choice of arrow on this black line. So now we haven't talked about what these operators are. This is a qubit, this is a qubit, but now we have these things. And what that does is that kind of tears apart this gauge structure down to a Z2 dynamical per qubit, which is just given with whose Gauss law is the fermion parity projection. And then a Z2 background for Majorana, which is the choice, which corresponds to the choice of all these arrows. Oops, sorry. So the key point here is that, and this part is hard to understand, but you'll see an example in a second, that here we kind of have done this mapping, and we end up with a Z2 cubed per qubit. And so sorry, I should say that here we just remove this by, assigning, say, blue to Z and yellow to X. And so now we're just left with the choice of arrows, which we know is the Z2 cube. Okay. But this Z2 cube, this is not intuitive. This Z2 cube becomes a Z2 per qubit and a Z2 per Majorana when we actually add these additional, because when we add these black links, we add additional Z2 degrees of freedom. Background Z2 degrees of freedom. So let me show you how this happens. So first of all, we have this dynamical Z2 gauge field, which is the fermion parity projection. And what that should do is that should enforce that this Majorana pair corresponds to the same operator as this Majorana. So that's saying that tau 1 times tau 1 prime should, tau 1 and tau 1 prime should be the same when acting on a physical state, which is just the product of all 4 Majoranas. And it's the same constraint that says that opposite edges should be the same for any pair of opposite edges. So this is a conventional Z2 Gauss law constraint, and it's a real gauge field. It's not like we're simulating the gauge field. It's really, well, really there or really not there. Now,
What does that mean?
well,
What do you mean it's a dynamic equation?
yes, what I mean is that there's a Gauss law projection, and there's fluxes of this gauge field, and there's in a very conventional. So you're about to see the full Z2 gauge theory come out. So you have the Gauss law, that's the fermion parity. But now let's talk about these black links that I introduced. These are links between Majoranas that touch different qubits. These operators are not gauge invariant. And the reason they're not gauge invariant is that they anti-commute through this Gauss law. That means they don't correspond to anything physical. But let's go back to some standard Z2 gauge theory. That means that the operators on these links, they are these are qubit operators, right? They square to 1. They're like a Z operator for an effective qubit that lives on this link. This is literally the operator for a Z2 gauge field. It anti-commutes with the gauge constraint. And it can't be physical. The operators just on this black link, they're guaranteed to take you out of the physical space. But that's okay, because that's exactly the situation in a real gauge theory, in a quote-unquote real gauge theory. Good. So let's start to write codes. So here we have a bunch of qubits with a bunch of arrows. Actually, if you count the Castellan condition satisfied, but please don't try. But it is, I hope. And so that means every face actually has an odd number clockwise. And
Sorry,
here,
can you explain your comment from the last slide? So you said, okay, this takes us out of the physical space, but that's good, or
it's correct because so in a gauge theory, the vector potential is non-physical. What that corresponds to in a lattice gauge theory is that the link variable on its own is not physical.
right?
But well, as we're about to see, you can build something physical out, which are point-to-point flux. So I'm actually going to re-emphasize that again. So these black link operators are odd under this Z2, under this Gauss law. So they take you out of the physical space. They're not allowed. And the way that you see that is that they flip. They anti-commute under that Gauss law constraint. But let's say that I took these two. these two are the product of these two operators. The product of these two operators commutes just fine with this Gauss law, because -1 times -1 is 1. But now I have a problem with this guy. So I just take a loop. This thing is physical. Now, so these chains are Z2 invariant, which means that they do correspond to some operator in the physical space. Now, what's really nice is that you automatically build stabilizer code this way, because none of the black lines, none of the heavy black lines touch each other. That means they all commute. So in the Majorana space, they all commute, which means under perfection, both physical operators, but also ones that commute. So here what we've traded is that kind of commutation relations are trivial. It's very easy to build a large basis of commuting operators. It's harder, sort of, to see if things are physical. It's not that hard. For example, this is physical. Now, let me just talk about stabilizers for a second, so we can draw the qubits this way. And we can take some four-body operator. Actually, this four-body operator corresponds to this loop under the Majorana. I've suppressed the arrow. But if you put the arrows back and you satisfy the Castellan condition, then if you take the product of the black links around this loop, you will get XZ. And if you do it everywhere, you'll get a bunch of commuting state. So actually, this is kind of like a picture of a state. Now, these things, these BPs, we call them BP because they're fluxes, and they all automatically commute. And well, I should emphasize that preparing certain stabilizer state, for example, these is very efficient on our device, and in fact, we use them for error correction. But this you should just think of as a picture of the state. This actually defines a unique state up to a global phase. It's just drawing a picture of all the observables for that state. And if you're in eigenstate +1 of all of these loops, that's a unique state. So if anyone's familiar with the planar surface codes, this is an example of a distance 4 surface code. A distance 4 surface code, we can think of how it encodes a single qubit. Yeah. This is a picture of something that was drawn almost exactly as on the previous slide, except I've drawn the boundaries so that there's these extra dangling Majoranas. Now we know that the corners of these squares are dangling Majoranas. And what you see is that there's 4 dangling ones, and the space of 4 Majoranas conserving parity is 1 qubit. That's why this surface code stores a single qubit. Now, the logical operators, and again, if you're not super familiar with, planar surface code, maybe this part is a little bit too fast, but I'll just say for the experts in the audience that the logical operators that go from top to bottom are just exactly the fermion measurements between this pair of Majoranas. This, for example, you could call the Z observable. This you could call the Y observable, that sort of convention, and this you could call the X. Actually, it's kind of funny. You can see that the surface code itself is just a blown up tetrahedron. Remember, a single qubit is 4 Majoranas, and then you just kind of build a bigger diamond out of many little ones. And the code distance is actually set by the graph distance between the 2 Majoranas. So this is a distance 4 surface. Now, let me quickly say how we use this to do error correction. So again, the model you should have in your head is 4 Majoranas separated by some code distance. And what we do is errors will flip these fluxes. This flux is that Z2 gauge, this flux is the flux of that Z2 gauge theory. And what we actually do in the experiment, I'll go through this kind of fast, is that we have this square grid of qubits, and what I've drawn is the physical location of the qubits along with the couplings that they have. And the reason that we choose this geometry is that we put a surface code on it. So now it's very easy to draw many surface code. This is another one. And what happens is that as what we do is we couple in some order these qubits to the ancilla, and we measure the flux. And it could be +1, or here I've given an example where it's -1. So what happens is that you should imagine that what errors do is they create fluxes in pairs. So here, for example, whatever Pauli operator the yellow lines correspond to, if we act with the yellow lines, that anti-commutes with the blue lines, and so it'll create a pair of fluxes. Those 2 fluxes will show up as errors, and we'll detect them. And maybe there's another error which kind of shoots it out this way, and you can see that the errors just go along the boxes. Maybe we have just one stabilizer violation here, and then maybe you would guess that this is what happened. Okay, we can have multiple errors. And so let me just quickly, yes.
I guess I just want to back up and get a broad picture, I guess, what we're talking about here. So we started out by essentially associating 4 Majoranas to every qubit into this tetrahedral structure that has a lot of different it has a lot of symmetry to it. And then you basically reduce the symmetry by applying sort of the arrow directionality that you impose. There's also a couple of other constraints that reduce it to this planar form. And then essentially you're saying that you're using this planar form to more simply think about sort of which operators go into the stabilizer measurements that you need for these for this sort of logical qubit here. So if you sort of know the order of the x's and v's just by the order of this planar diamond around each qubit. That's the way to think about this.
I think that's, yeah, I think another way to say what you're saying is that so there's an embedding of qubits into Majorana's where like you can think at different levels, but the easiest way is to just imagine that you do the embedding and then do things which are kind of allowed by all the gauge symmetries and project at the very end. So you just think of the system of Majorana's and then you kind of don't worry. You worry at the end if what you did was physical.
But
And good. So what that does is that gives you a way, for example, to draw a stabilizer code immediately. So this is, you know, immediately this is a picture of a stabilizer code. You know that these loops.
and it tells you sort of which operators, every single operator that you then when you convert back to qubits,
Exactly.
you're actually working with.
It tells you how to get the operators. It tells you also the code distance. I haven't shown you yet why the code distance for this in these Majorana's, but it is. And it also, so we haven't gotten to braiding yet, but this is just the memory. This is promising that if you separate these Majorana's, here they look separated.
Yep.
And the point is that they really are. And the way that you enforce that separation is that, yeah, when you have errors, you measure these fluxes. And so what does the memory experiment actually look like? Well, maybe we start in some very nice surface code with all this +1. That's not what we actually do, but that's a decent model. Now some errors happen and another error happens. And now you have separated syndromes. And then what we do is we try to guess what happened. You know, maybe the green thing happened, but another valid error history is the blue thing. And so we have to guess. And it actually, this is an example where we could guess either the green thing or the blue thing. The green thing is the thing that happened. You know, I mean, you don't know what happened. You just have these red squares and it's consistent with blue or green. But maybe if you think that errors are relatively unlikely, green is more likely than blue because green had 2 errors happen and blue had 3. So then what we do is we guess that green happened and then we would decode it correctly because what we do is we would bring these fluxes back together along this path. Okay, I don't want to talk too much about that. We have a lot, you know, we have 2 now big memory experiments. You're welcome to look at those. Here we're focused on braiding. So what we've explained is what we've talked about so far is the dynamical gauge field per qubit that's associated to the fermion parity projection. We've been suppressing the error of most of it. Okay, so now we are left with the arrows. So I told you about the Caslin orientation. And on a single qubit, it was very natural to have this Caslin orientation. But if we extend this to the entire graph, so we have some planar graph, and we insist that an odd number around every face are clockwise, we get some very convenient stabilizer rules. And we actually get all of the individual surface codes and all that stuff. But okay, again, if anyone in the audience is super mathematical, actually, you don't need this Caslin condition on the black edges. It's just convenient and it matches the surface code convention and you may as well pick it. But in any event, you have to choose some orientation for these errors. Again, we choose Caslin. And what happens is you can flip all of these arrows according to the Caslin without changing the Caslin condition. This is again, you know, Caslin conditions are constraints on loops. And so if you flip all the arrows around the vertex, you don't change the Caslin condition. And so this is another gauge constraint, or not a gauge constraint, another gauge transformation. It was your choice to put these arrows. They're not sort of physically dictated. Now, you might think that they have no physical meaning, but we're going to see that they do. In any event, you had to choose them. So this is like a background gauge where no one forces you to take a particular value of the background gauge field. But based on, you know, if you try to measure the field in certain places, you'll notice that no matter what consistent choice you make, it'll satisfy the properties. And in particular, if you choose this Caslin orientation, then no matter which Caslin orientation you pick, which is invariant under the slope of the arrows, if you take this line and you take the product of the arrows around this line counterclockwise, you'll notice that they actually count the number of enclosed Majorana's. This is why the Majorana's carry a flux of this background arrow gauge. This is the flux that gives them the non-Abelian statistics. Now, let me sort of implore you to take the gauge theory even more seriously. So the basic operators in the theory of Majorana will be bilinears, but it's generally unphysical because it intercommutes with the constraint. But there is a physical analog, which is just like in normal gauge theory, it's a Wilson line. It's an operator which keeps track of the parallel transport of the gauge field between the two Majorana's. And you could also have a Wilson line between a Majorana which is bound to another Majorana. And this actually gives you the first example of some topological fusion rule. So this says that here, this is called a fermion in the surface code language. And it says that a Majorana can absorb a fermion by just applying the operator corresponding to this Wilson line. So the important thing about this Wilson line, and the reason again that this is just consistency with the gauge theory perspective. If you move, and this partially answers Charlene's question about the second Z2. If you move this red anion without creating any flux of the other gauge field, so we assume that we don't create fluxes of this other gauge field that I was talking about before. Now we're only talking about the parallel gauge. So if we move Majorana without creating fluxes of any gauge fields, then that unitary conjugation has to take this Wilson line to some other Wilson line over here. We can use that. Oh, so here, someone asked about how, a formula, which I'll skip, but the point is, yes, this can be read in the paper. There is a formula. You just draw the line along this graph and you get a particular Pauli string. Oops, sorry. In this case, here's the Pauli string, but there's a formula. It's maybe not so important because I want to emphasize the Majorana picture. So here, the point is that the Majorana picture lets you go from this ugly microscopic thing, where you have to keep track of the arrows and worry about the Wilson lines, to saying that, well, if I take the Majorana around, if I take this Majorana around this guy this way, or this way, I'll get a difference because of the enclosed Z2 flux. And so this is, again, just emphasizing that the difference between these two Wilson lines measures the flux carried by this Majorana, just like it does in the P plus IP case. So now we can be very practical. This operator exchanges Majorana operators, but it's unphysical, but we can just exponentiate the Wilson line. Actually, you could, if you want to find these operators, a convenient thing to do is just to insist that you do this and imagine that all the black links are just +1. But anyway, if you want to take Majorana 2, if you want to take Majorana 1 to position 2, then all you do is you just exponentiate this Wilson line, the exchange. You just exponentiate what would be the physical version of this operator. You have to follow this line, you exponentiate it, and it actually does move this black edge over, and you get the Majorana to hop from 1 to 2. And the same thing here. You can just imagine these edge moves. You get the Majorana here to hop from 1 to 2. So this just gives you a concrete circuit. These are Clifford gates because the Wilson lines are always Pauli string, and this is an angle pi over 4. So maybe for people that are sort of more embedded in the topological way of thinking, you can see the fusion rules. For example, sigma cross sigma, which are the two Majoranas, give you either a fermion or the identity. The way that you see that is that if you just have two Majoranas here, you could imagine removing them by adding this black link. And so if P prime is +1, then the split could either both be -1 or both be +1. And I want to say that, yeah, so there's these Wilson lines, and you can always think of the surface code in this way, but this is a much more general code. You can move these things into the bulb, and there's reasons to do that both for denser memory and to do gates. Now, let me show you just in terms of these Majorana moves, braid generator. So what we're going to do is we're going to take this Majorana, and this is just to show you the utility of this picture. It's quite simple to exchange this Majorana with this one. And all you do is you just take these little hops. So you move this, so the plan is to move this Majorana over to the left and then upwards. And you can use these Wilson line formulas just to give you the circuits that do this. And so this would be a full exchange of these two Majoranas. So 1, 2, 3, 4. You can actually do this, use this to do fault-tolerant gates. And every single move is just given by an exponentiation of those Wilson lines. You actually don't have to worry about projecting back down. You just do everything in the Majorana picture, and then you can project the gates at the end if you like. So this is a braid generator, and once you have this, you can do the full Clifford gate set fault-tolerantly by moving these Majoranas around each other while keeping them far apart. Actually, we were able to do something a little bit more aggressive. We were able to make a GHZ type, so a GHZ type experiment where we have 4 Majoranas on the boundary and 4 Majoranas to bulb. That gives you 3 qubits because you have 4 pairs, but 1 fermion parity constraint. This is our choice of logical operator. This is our choice of logical operators. And we actually did it. So here what we did is we just, we did actually the dotted grid. So we exchanged these two Majorana's for convenience. We actually created a GHC state inside of this 8 Majorana, system. At the time, we weren't doing error correction on this. The GHC state is not a perfect fidelity. Still, this is an entangled state of 8 of those Majorana qubits. Okay, great. So I think that for the sake of time, I'll sort of stop here with the Majoranas. Maybe I'll take questions about them at the end. Let me quickly advertise that, you know, that was kind of talking about a real gauge theory that lives in the qubits, and we made use of it in trading. It's really there. Now we can ask what we can gain by simulating. So now we use qubits as gauge theory, actually. And what we see here is these are two systems, which the initial state is different by a single qubit gate. Actually, the initial is equal to 0 here, but there's two initial states which are different by a single qubit gate, and they both have an energy buffer up here on the top qubit. And the statement is that this is going to be a demonstration of localization without disorder. Actually, unitary, which inside of it breaks no symmetry. Of course, this system doesn't really have translation symmetry because, okay, this is the geometry that we have available to us. But we also do a 1D example, which is truly translation invariant. So the unitary, neither the unitary nor the initial state break any translation symmetry, break any symmetry at all. And yet you get localization of energy in one case, and here the energy is spread out. Actually, it's spread out by cycle 4, so we omitted by accident the initial state, which does have an energy bump in both cases.
Sorry, what are you actually doing in these circuits?
Yeah, sorry. So
now my physical variables are on the links.
the physical variables, they're actually on the dots and on the links. Maybe let me get to it. What you should imagine is that this is a picture of energy density, and orange is more energy.
Okay.
And what we're missing here is that before time step 4, actually there's an energy bump over here as well. So this is orange in the previous time step. And actually it very quickly spreads across the whole system. So it thermalizes, whereas this one stays localized. And the puzzle is, how can you do this without any disorder in the initial state or the unitary? So I'll quickly explain how you can do this. We're motivated. I'll just say that maybe to this audience, it's not really useful to spend a lot of time saying why we should study disordered quantum systems and localizing systems. But I will say that actually this is another application of lattice gauge theory, at least to give you a convenient way to study these disordered systems. So let me quickly say, one good guiding principle is to, sorry, how many minutes?
-4.
-4.
Oh, I thought it was loud.
I thought I had an hour.
Oh, with questions.
Okay, let me go very quickly. I did start by that. But anyway, so let me say that, okay, this is just kind of fun, so I'll quickly say it. An undergraduate might say, well, disorder leads to localization. So let me just put some disorder. I have some system where everything is qubits, and I want to call these open circles my potential. So he's going to put some disorder, or she, and then here she's going to say, well, I can have a different disorder configuration. And then, this is an undergraduate, they just learned about quantum mechanics, so they learned about superposition also. And so they say, well, each particular disorder configuration is different. But, if I could superpose potentials, then that overall superposition is translation invariant, because any disorder configuration and its translate will be in the set. And there's another sort of approach to this where you say that, okay, well, actually, we can have a potential insights. And we have a coupling, which is given by some coefficient in front of an operator. But let's say instead of, that coefficient being a number, we made that coefficient an actual operator. And we sat in a superposition, say in the 0 state, and we measure this by x, then you can think of each branch of the wave function as being governed by a Hamiltonian with different signs in front of each operator. And there's a hint of gauge symmetry, which are that these operators should be with the Hamiltonian. So what does gauge theory actually give us? It gives us an efficient implementation of the thing I said on the previous slide, that in a gauge theory, the background charges are infinitely massive automatically. So if you take a gauge theory and you sit in a superposition of all the charge sectors, then in each charge sector branch, you actually have a definite random background potential. And these are guaranteed not to move in any branch. And it just turns out that this gives you an efficient Hamiltonian. So I'll just mention that, okay, last time we were talking about sort of a pure gauge theory, but the Majorana particles here, our actual model is that we have matter living in the open circles and gauge fields living on the diamonds, but this is the actual geometry. So there's qubits on both the diamonds and the circles. These are the allowed operators. This is the Gauss law. Okay. Okay, so there's some duality, which I don't have time to discuss, but the point is that we actually get, well, there's a dual description, which is good for theory, but the point is that this is kind of the model that we can consider. It's not integrable, but this model is a local energy density. Maybe ignore these, it's just, ZZZ, XX. Yes, so I'll wrap up, which I'll say that, we can create energy excitations, and the point is that in this model, very quickly what we can do is we can create energy bumps at time equals 0. So this is perfectly translation invariant, the state is translation invariant, the unitary is translation invariant. You do a single qubit rotation at the start, and in one case, you thermalize the energy, and in the other case, the energy density stays localized. Actually, on the newer chips, we're able to go out for longer time and see that this location. Okay, and I think I'll end with the 2D example and stop there.
For the localization example I'm talking about now, if I make a generic perturbation to like either the initial state or to the circuit, do you expect localization to this?
A generic perturbation to the initial state, localization will persist. A generic perturbation to the circuit, well, in a finite system, yes. In an infinite system, we don't know. If you make a perturbation which is gauge invariant, then yes, localization persists.
Localization is different. So usually when we think about it as a predetermined localization, not.
So this model is already interactive. Is this not an? So there's a local. So there's no evidence that localization would do this. Well, okay, you could call Gauss law. I mean, the model is not integrable, and it's not integrable in any background charge sector. In the 2D case also. It's the model is never integrable in any fixed background charge sector. But it is but it's true that if you perturb away from the gauge theory, violate the Gauss law, then we don't know. And of course, we're not making, so just to be very, very clear, we're not making a statement about localization in some infinite time limit. We're making a statement, actually, this experiment is nice, let me advertise it for a second, in that we have a clock, which is that, well, actually, again, here in the paper, we show more time slices now. But you can actually see the energy bump in both cases kind of start to thermalize. So here, here it completely thermalizes and it's gone. In the case where you're in a definite translation invariant background charge. Here, when you're in a superposition of background charge cycles, it persists for all time. Now, we obviously can't run for infinite time. We don't make a claim about that, but we have a clock, which is the thermalizing system. And the clock is fair because we start with the same energy density and with the quasi-conserved Hamiltonian, and we have the Trotter-Rotation, so it's not exactly conserved, but it's close. We can check energy conservation. And moreover, the circuits for these two experiments are identical. So that's sort of the area where we can make statements. And this thermal, this sort of persistence is robust to perturbations that preserve the gauge. Yes.
So the first part, so if I have a stabilizer code which in terms of qubits, that comes with constraints on what the density of information and what allowed gates are.
Yes.
So here you get formalism where instead of thinking about it in qubits, I can think of this expanded picture of Majorana's. I can understand the usual graphical operation. You already think of it, but there's this kind of different gauge theory with Majorana's. But then the Majorana formula also helps to do non-stabilized.
What do you consider to be a non-stabilized?
What's
like that?
What's an example?
Like, would you consider a general string net? I just don't know what you mean by stabilized. Like sometimes
it's something
people call
that
string nets non-stabilized. Do you mean non-polystabilizers? Or you mean something where the stabilizers are changing, or do you mean?
Well, something which is non-commuting projectors.
Oh, not commuting projectors.
Yes.
The Myronas do actually help you with that. We don't apply them in this way. They're already useful if you just restrict commuting projectors. For example, you can get higher memory densities than, again, not in terms of scaling, but you get higher memory densities than the surface code by using the same number of qubits and packing the Myronas to the bulk. You can get more efficient gates by abrading in some cases than by ladder surgery. So if you think of the Myronas as dynamical, even in the context of these 2D local codes, they're quite useful. I will also say that there's many sort of results about how 2D local Pauli codes are stacks of surface codes.
Exactly.
So all these codes can be written as Majorana codes. Actually, these are, again, more general because you can have bulk Majoranas, and so it covers more cases. Now, of course, in 3D, if you have a 3D local code, then the Majorana description, although it in principle, well, it doesn't actually look, it won't work exactly like this because it's actually very special to have a code which can be written this way. And you don't expect it, in fact, it doesn't work for 3D local codes.
No, I appreciate that. I guess I'm still kind of missing the point because I already think of codes as gauge. So what does it bind me to think of it as this expanded gauge?
Well, I mean, it depends. So it depends. If you were thinking of the surface code as like a lattice Z2 gauge theory, this is just a completely different perspective. So for example, I mean, if you build, well, what I can say is that these codes are just, if you put Majoranas in the bulk, are just not they cannot be written as a Z2 gauge theory. They just can't, as that Z2 gauge theory.
Yeah.
So it just gives you more codes. Now you could like.
But all of them are going to be equivalent to copies stacks of Yuri.
No,
Stacks.
no.
Still can leave more of
Okay,
the
sorry.
In this last experiment, are you doing any, I mean, obviously for all of the stuff with the error code, you're doing lots of projective measurements, that's enforcing gauge constraints. Are you doing something to enforce the gauge constraint when you have these physical?
That's a good question. So our shutterization exactly preserves the gauge constraints. That's one thing we're doing.
Okay.
When we can post select on the gauge on the so at the end we do terminal measurements and we look at the gauge constraint.
So you made a comment about the fact that the charge sectors are separated by infinite amounts of energy. At some point, you said that
Or they don't interfere.
They don't interfere. So I understand whatever when you get a projective measurement of only looking at one charge sector.
You are sort of looking at just one charge sector, at least locally. So if you measure, say you measure something locally, then the rest of the system hasn't determined this charge sector yet.
Okay, let's leave more of